recording now. Cool, kia ora, everyone. And thank you, Anna, for the introduction. So yes, I'm just going to talk about some of the things binaries do, because since I arrived in Auckland, I've really put together quite a remarkable code to be able to study how binaries impact everything in the universe. It was kind of obvious when I was doing my PhD all the way back into, well, I started in 2001, that eventually, binaries are important. It's kind of interesting that over a lot of time, astronomers have had trouble thinking about binaries and including them, because it makes evolution and the story of stars much more complicated. A lot of the work I'll be talking about has been in collaboration with my main collaborator, Elizabeth Stanway, and the BPASS team, who I will introduce all of those later. And of course, this is supported now by a Marsden Fund grant, and it's always been supported by the University of Auckland and the University of Warwick. So let's click on. So Anna's already introduced me. Who am I? Yes, I'm Associate Professor JJ or Jan Eldridge. I don't mind either name. Pronouns are she, her, or them, they. Typically she, her in person, and them, they if it's in print, although I'm still trying to work that out. I am an astrophysicist, so I still do physics. I'm just using the stars to try and do those experiments because, it's very difficult to make nuclear fusion go on Earth, but it's very easy in stars. I mean, we don't actually have to do anything for a star to do nuclear fusion. So that kind of makes things very easy, but difficult in other ways. All physics is difficult in some way, but that's the fun part of it. So yes, then I study exploding binary stars while exploding the myth of a gender binary. So for those of you who don't know, I am transgender, which just means my gender does not assign with the sex I was assigned at birth. And I'm open about that. So because you're going to meet trans people around in your everyday life, although not during level 3 or level 4 lockdown. And we're just normal people. That's the main thing to try and understand. And I work on stars, galaxies, supernovae, gravitational wave events, long gamma ray bursts, all of these things. And you can follow me on Twitter on astro_JJE. Feel free to tweet along if you want to comment on, oh, astro_JJE, she's so boring today. I might be boring. I'll try and be interesting. So who is the BPASS team? Back when me and Elizabeth started out on this, it was just me and her. So I was a theorist and Elizabeth is an observer. She spent her PhD looking at high redshift galaxies, which back then in like the early 2000s was a redshift of 3. So that means the light from these galaxies is so distant that its wavelength has been increased by a factor of 3 over the time it's taken for that light to pass to us. So in theory, those galaxies are now receding from us at like 3 times the speed of light. But of course, now we've pushed this back, and so now we've actually got fainter further and further. So now we can see galaxies back to around about a redshift of 6 or 7, sometimes even further. And here she's posing with, I think, the ATCA array, which is in Australia, which is radio telescopes, because when you're looking at these very distant galaxies, radio is one of the only ways we can actually access and try and understand those galaxies. So recently we've been joined by Heloise, who's a postdoc here at the University of Auckland. She finished her PhD in Sheffield last year. I think it's just over a year ago. In fact, I think she had a viva. She'll tell me I'm wrong later, I'm sure. But she's been developing Hoki and trying to make it easier for people to use our work, as well as trying to actually do something extremely hard, which is, well, we'll get onto that at the end, but it's to do with trying to understand how old stars are, because it's something we've wanted to look at with BPASS, with these binary populations we create for a long time, but it's extremely difficult. And now we have Heloise, who's going to be able to actually study that and help us. There are 2 past PhD students who some of you may recognize, who is Lynn and John. They both now have postdocs and did a PhD with me in Auckland. Lynn did some quite important work trying to understand the nebular emission, which is where you have the young stars and they heat up gas around them and they produce very characteristic emission lines, and binaries make a big change on that. Whereas John was looking at neutron star kicks. So this is how fast neutron stars get kicked out when they get formed in a supernova. Now we've also been joined by Max, who's comes from the Netherlands. He's currently doing a PhD, and I'll mention his work towards the end of the talk as well, because I've tried to put the more recent stuff that we're doing on gravitational waves towards the end of the talk, because as you'll see, his work Petra's work, Sohan's work, Wouter's work, and Sean's work, and Gleb's work all come to this point of where we're trying to get to for the next questions we're trying to answer. So yeah, Max is looking at cosmological simulations and using BPAS. Petra is looking at white dwarfs and other compact remnants in binaries for LISA, which is a future gravitational wave mission that's going to be based in space. Sohan and Wouter recently finished their masters, and I think they're still eagerly awaiting their results. But they both worked on parallel projects that we're trying to combine together to a neat piece of work I'll get onto later. Sean is currently doing his master's thesis on neutron star binaries, looking at their mergers, but also what they look like before they merge, because we can see these double neutron star systems in the galaxy. So it gives us something else to constrain against, as well as the number of neutron star mergers we see in gravitational wave observatories. And Gleb is an honours student who's doing work with trying to work out how old star clusters are, which is kind of important because, again, binaries mean we have extra information on how old a star cluster is, and we're trying to calibrate our models to see if we're right, because if we are, then there could be bigger problems than we've actually thought about with some of the things we're doing. We've also got many other past students. So Ashley Crimes is a PhD student from the University of Warwick who's just finished his PhD, and I think he's moving on to a postdoc shortly. Leon, Georgie, Mason, Lillian, Nicole, Lucas, and Winda are all students who have in some way had a contribution to BPAS, and actually we've been working with them for many years. And there's so much we've done, I can't talk about everything in one go and make it sensible. But you know, there's a lot of work for students that have gone into this, and without the students, I don't think me and Elizabeth could have actually achieved quite as much as we can do with this wonderful team we've had. One slide I always like saying as well is, why do I do astrophysics? Well, for those of you who know me, you know it's because I watched too much science fiction when I was younger. And of course, it's very obvious now why I like Doctor Who, because, you know, they're wonderful, all 13 of them. Now, those of you who are numerically nimble will look at this and go, but hang on, there's 14? Yes, that's Doctor Who. It's wonderful, isn't it? How complicated that it isn't. So yeah, I mean, this is good because also in science fiction, you can look at science fiction, especially when you're an astronomer, and try and understand what's going on. And not so much always do the thing which is very easy to do, to say, oh, that science fiction is rubbish, you know, that can't possibly work. Maybe it's, how could it work? You know, with our current understanding of science, could these things work? And that's a much more interesting and difficult question, and perhaps more revealing question that I like asking in lectures when we're trying to teach things, for example, like Newton's third law or general relativity. It can be very interesting. Anyway, I'm going to start now by actually going back to the astrophysics, and to change tack a little bit, I want to start by looking at the big picture. Now, there's this wonderful quote that I learned a few years ago from Celia Payne-Gaposchkin, and it's from a lecture she gave for the Henry Norris Prize lecture she gave to the AAS, which is the American Astronomical Society. Now, the interesting thing is she gave this lecture in the year I was born, and this is the quote down here, which is, the reward of the young scientist is the emotional thrill of being the first person in the world, in the history of the world, to see something or understand something, which is what it's like to be a PhD student or a master's student or an honours student. You're working right at the coalface trying to solve this one problem. But what's happened to me over the last few years since I've done my PhD is you end up getting the reward of the old scientist. Not that I'm old, but you become more experienced at least. That's the sense of having seen a vague sketch grow into a masterly landscape, because now I'm looking above, and with so many students working at individual projects, you can see how you're pushing back the knowledge of this landscape you're trying to create. And hopefully with BPAS and in this lecture, you'll get an idea of a sense of how, even though I'm going to talk about specific projects, they give you an overarching view of our landscape of the universe. It's also interesting here to note that back in 1977, he and him was used as a general neutral pronoun, whereas of course now you rewrite that saying them, they. But it's just funny reading this by Celia Payne-Gaposchkin. And if you don't know Celia Payne-Gaposchkin, she's the woman who wrote the first PhD thesis for Harvard, which was on the reversing layers of stars, or in other words, the atmospheres. And she was the first person to calculate the fact that stars are made of 70% hydrogen, so a very different the abundance of planets. And that was one of the first things we needed to know to actually really start beginning to understand the universe, which is this picture. Now, it's really great of Richard to put this picture in last week, because he would have talked way back here if I get my mouse pointer, about the early stages of evolution of the universe, which are interesting, but most of what we understand about the universe comes from all these other things in here, which are the dirty bits of matter that shine in light and like pollute the universe, pollute that nice clean universe that would be so easy to understand without it. But stars and galaxies give us probes to actually understand that universe, because, you know, through trying to understand stars, we can understand the galaxies within them, and by understanding the galaxies we can understand the expansion of the universe. And also by studying the abundances and how they change within the stars and through the galaxies, give us an idea of the age of the universe, and also just give us much more understanding about things beyond just understanding the stars and planets. Not something I do myself, but it is a tool we can use. So actually understanding the stars and the planets and the galaxies in as much detail as we can helps us understand the universe in greater and greater detail. Now, the reason why I'm showing this image is because it's how I started to take you through how BPAS has helped us understand different parts of the universe. Because I started out my PhD studying today, over here on the right, with my supervisor Chris Tout in 2004, when we was looking at stars that go supernovae. And by 2004, there was enough images of stars, galaxies taken with the Hubble Space Telescope, that when we saw a supernova go off in a nearby galaxy, there would be an image of the star before it exploded, which is a very exquisite constraint. And from that work, we've been able to show that most stars exploding are red supergiants, like Betelgeuse, although Betelgeuse is not going to explode anytime soon. But after my PhD thesis, Elizabeth was looking at high redshift galaxies, so over here on the left. And here there was a problem, because the standard stellar populations that that we see in the galaxy today did not look like those we saw in these high redshift galaxies. And immediately we thought the answer was binaries. And then we found out eventually that it was binary stars causing rapid rotation. And so the two things together were causing or explaining why the stars look the way they did at high redshift, like some of the earliest galaxies were different to those today. The problem is the referee didn't like our paper and said, you need to calibrate it on the nearby universe first. And so this is why we have this paper in 2008 and another one in 2009, where this is where we began what we term spectral synthesis. So not just trying to predict how many stars, how many binaries there are, but what they look like if you observe them with a telescope. Because one of the problems in all physics, in all science, is you can have a model and you have an observation, but where do you match the two? Do you try and infer as much as you can from the observations to go towards the models, or do you take the models as close as they can be to the observations? Because we know everything about the models, it is probably better to take the models as close as you can to the observations. Because you don't know everything about the observations, taking them down to the models, you may make some mistakes. So that's really what we started with here. So we started out in the nearby universe, made sure our models made sense, and then we could try and look at the far redshift universe and show that the nearby universe models didn't fit here unless we put in binaries and rotation. And then we realized that our code needed to be improved, right? Whenever you compare a model to observation, you know you can do better. And there's always some way you can improve what you're doing. And so then in 2016, we worked on version 2 of our code. It was much better. I'll get onto how much better later on. And we went back to these high redshift galaxies to explain a period called reionization. So early in the universe, there was all the hydrogen, all the elements were ionized, and then you had ionization where all the electrons and the protons combined together. And so you have the dark ages. Then stars formed and started ionizing or reionizing the universe, so it became ionized and you could actually see through it. There's a question about where all those ionizing photons come from. So these are photons with wavelengths or with energies above 13.6 eV, because that's the energy it takes to ionize hydrogen. We basically showed in 2016, along with George Becker, that these all come from binary stars. And it was a known problem that if you assume that every star is single, you just don't get enough ionizing photons. So people were looking at things like supermassive black holes accreting, producing the radiation. But there's a problem with that, because how do you have massive black holes when you've only just got stars? And so with the binaries, because of the different processes that goes on within them, you can actually get more ionizing photons. And now the simulations, when they put in our models, show that you can reionize the universe very easily if you include binary stars. So that kind of means the universe is only transparent because of binary stars forming early in the universe. At the same time as us having this study on reionization, the detection of two merging black holes by gravitational waves came out just a few months afterwards. And so both myself and Elizabeth wrote another paper, because our models are so adaptable that not only do we predict what they look like, we also predict how big the black holes they form. Are they in binaries when they both form? Can they merge within the age of the universe? And so not only could we reproduce the masses of the observed gravitational wave event, we were able to link the fact that gravitational wave events we see today are actually those coming from stars that formed all the way back here during reionization. So this is one of the landscape pieces. It's like, even though you've been looking at reionization down here on the left-hand side, over on the right-hand side, I'm hoping you'll see, yes, you would see this at the same side, on the same way. On the right-hand side, you then observe them today as gravitational wave events. Now, this is interesting because two very different type of observations are constraining the same physics and the same models that you're trying to use to understand the universe. Now, this was only our version 2.0. We then had the version 2.1 paper. We're actually up to version 2.2 now, because again, we keep on improving our models. And actually the things we've done are to improve the very old stars when they get very old, like our, well, even older than our sun, when the stars approach the age of the universe. But we've also added in more single stars. Not every star in the universe is a binary. And actually changing in these things, trying to make our models more realistic, always improves the match we have between our models and those we observe, well, observations. So actually that was these two papers where then we started looking with version 2.2, what happened with reionization, and also, with improving our models by adding in more single and improving the older stars, and also looking more at gravitational wave events through the history of the universe, which we'll get onto later. But then since then we've had many, many more papers, and I probably left a few off here, and it's just, I can't believe when I made this slide that it was that many papers. And I've probably even forgotten some, and it's just because we've put all the effort into writing this 60-page paper and creating a tool. And now we're very much in this process, in this phase of trying to use this tool to understand the universe in as many different ways as we can do. For example, this is neutron star kicks, this is supernova light curves, this is nebula emission, this is an entire galaxy trying to measure its distance from its supernova rate. This is again looking at gravitational wave transient rates, this is looking at long gamma ray bursts, this is looking at the errors in the binary fraction, what happens if you have more or less binaries. This is Hoki trying to improve the how easy it is to use BPass, and also trying to look at ages of stellar clusters. And these two are, one is on that black hole that isn't a black hole, and the other one is on trying to use red supergiants to age clusters. So there's a huge variety of different science now we can do with this. And it all comes about because of the binary population and spectral synthesis code we have. And we developed it. It seems like we developed it to study all these things. It's just we just tried to take a very good approach to begin with, and it just turns out we can use the same set of models for lots of things. And we know there's uncertainties with what we're doing, but let's take our best guess. We don't tune it, as some other systems do, and see if we can be less wrong than modeling the universe than if we assume every star is single like our sun. We know 50% of stars in our galaxy are in binary systems, 25% are in triples, or quadruples, or quintuples, so even higher order systems. Only a quarter of stars in the galaxy are single. So this is why it's important to have this code. And we're also trying to be the theoretical equivalent of multi-messenger observations. So we make one model of the stars, and we observe them in every way possible, or we take them as close to observations. So for example, gravitational wave events, as well as predicting what they look like if you observe them through a telescope. Version 1 was based on like 15,000 detailed models, but in version 2, where we're now running, has 250,000 models. And the key point here is they're detailed. So we're not making approximations as most other population synthesis codes do. We compute the full structure of the star from its center to its surface, which means that when it starts losing or gaining mass, we know how it reacts to that, which means also that when we get to the end of the evolution of the star, if it's going to explode in a supernova, we have the structure of the star before it explodes. And we've now been able to actually take that and then blow it up in another code, which is called a supernova explosion code, and work out what the supernovae look like. And this is something that other people literally cannot do because they treat their stellar evolution in an approximate way. And many groups now are trying to catch up and have these detailed models. The issue is an approximate way, it takes like a fraction of a second to model the evolution of a star. For us, it's somewhere between 5 minutes to half an hour to model the full evolution of one of these binary stars, depending on what happens on its lifetime. The other details here are things we have lots of different compositions, which is to do with how early or how late in the universe they were formed. And we have all the different stellar masses from about 1/10 the mass of the sun up to 300 times the mass of the sun. So how do those single stars and interacting binary stars compare? So if you've taken Astro 100 or read many textbooks, this is a very simple idea of how single stars evolve. So you have your main sequence star is fusing hydrogen to helium. That's where the energy comes from. If the sun was gaining energy just by collapsing down smaller and smaller, it would only last for about 20 million years. But because it's getting energy from fusing hydrogen to helium, it has enough fuel to last for about 10 to 12 billion years. And the lowest mass stars can have trillions of years of lifetime. And the fastest stars to evolve, 300 solar mass stars, have a lifetime of about 3 million years. That's because more massive stars evolve faster, lower mass stars evolve smaller, but they're all slower, but they're all fueled by nuclear fusion. Eventually though, in the core, you burn all the hydrogen to helium, and so you end up with a helium core, and there's still this hydrogen envelope. The core size is about 10 to 20% of the entire mass of the star. It gets bigger the more massive the star is. But then in more massive stars, this helium core collapses down and then it can start fusing. And so then you start fusing helium to carbon and oxygen. If you try and squeeze two helium nuclei together, they last for a fraction of a nanosecond and then they fly apart again. But in the time that they're stuck together, a third helium nucleus can come along and then you can form carbon. And when you've formed up enough carbon, you can start having helium particles coming on to a carbon nucleus and forming oxygen. So normally at the end of the helium burning stage, you have a carbon oxygen core surrounded by a helium mantle. And then our sun will go that far. Stars up to about 5 or 6 solar masses will have one further burning stage where the carbon burns to oxygen neon, but they all end up becoming white dwarfs. So they just lose this hydrogen envelope and the core becomes an exposed white dwarf that we see if you go to Sirius B. Sirius A and B, it's a binary system. Sirius A is the bright star you see in the night, well, the brightest star you see in the night sky, and Sirius B is a white dwarf that's orbiting around it that you can only see through a telescope. But stars more massive than about 8 times the mass of the sun, well, okay, between about 8 and 13, something funny happens, but you still get a supernova. From 13 and above, you go all the way to iron, and when you've got an iron core, you can't get any more energy out, so it collapses down and forms a neutron star. And then that throws off the rest of the material and you get a supernova and you get a neutron star, which I'm trying to indicate here, flying off. Between about 8 and 13, it never gets quite as far as iron, but it does get further than oxygen and neon, and so you still get a neutron star forming and you still get a supernova. So that's quite simple. If the star is on its own, you've only got to worry about the core evolving and how much mass is lost in stellar winds. Very massive stars can lose the hydrogen envelope through winds, but they're very rare. The second you put a binary companion next to it, you start worrying about much more complex evolution because you have another star around your main sequence star, and depending on how close they are and how massive one is compared to the other, they can go down any of these different pathways. So for example, sometimes the stars can merge and you can get a single rapidly rotating star that goes on as it did do before, but now it's rapidly rotating. Or you can get interactions at different times. You can get supernovae, which mean maybe after the first supernova, the 2 stars fly apart, or maybe they're locked in the orbit around, and so then you get a black hole or a neutron star orbiting the other star. It gets complicated and mucky, which is why people have avoided this for so long. Because rather than just having to have one stellar model at one mass, you have to have hundreds of stellar models at each mass, with each mass of the other star and each separation of those stars. So that's why we have to have this 250,000 models, just because we've got to take account of all those different evolutionary pathways. And you can see here at the end, you end up down here in the bottom right, end up with 2 neutron stars or black holes together that can then merge in a gravitational wave event. which is the very latest stage we can get. So actually, binaries almost, you can imagine, just want to be single stars, because either they separate in the first supernova, or if they don't separate even after the second supernova, they'll eventually merge to become one. But you can only get these if you have binary stars. And the important thing here is with binaries, you get many more helium stars, because the interaction can drag off the hydrogen off the surface of the star, and you've got these helium stars. And we see these, the massive varieties are called Wolf-Rayet stars. The lower mass varieties are still hiding, but we know they're there. And that means some supernovae we can only get from binary stars, because otherwise you wouldn't lose that hydrogen envelope. So you get this new type of star that single stars can't do, which is one of the main key points about it. Now, this wouldn't be astronomy talk if I didn't show a Hertzsprung-Russell diagram. So this is how astronomers look at stars. And we have here on the x-axis temperature the wrong way, because yeah, I don't know. Well, somebody asked this on Facebook recently, and we was all going, we don't know why, but it's probably to do with what they was plotting originally on the x-axis as an observational HR diagram. But temperature is cool on the right, hot on the left. So blue stars are over here on the left, and red is over here on the right. So astronomers can't use taps because we think blue stars are hot and red stars are cold. So stars start off on the main sequence, they get brighter and slightly hotter, and then when they burn all their hydrogen to helium, they come across this Hertzsprung gap to become red giants. And single star tracks here are shown in black, and so this is what would happen normally. So most stars main sequence, red giant, explode or not. Very massive stars up here have strong stellar winds, and so they actually don't become red giants and become this other type of star called a Wolf-Rayet star. So that's what the black lines are, but the colored lines are stars of the same mass. So that's 40, 15, or I think 8 solar masses down here at the bottom. And the colored lines are all the different binary evolution tracks you can get if you've got stars in different mass ratios or different separations. It gets messy, because even though the general evolution is the same, you can see that for example, you can get more luminous stars if the stars merge, or if they accrete material. You can get less luminous stars if the two stars interact but don't merge. And actually the two stars that come down here, and if they lose their envelope, they then become these Wolf-Rayet stars or helium stars. And it gets very messy. And we're still trying to piece together exactly what's going on here and the impact of these things. One very easy impact I can show you as well is what happens if we take these models and we now explode them in the supernova code that I mentioned. And so here, if we had all stars that were single, they would all effectively, if they had hydrogen on, because these stars don't have hydrogen. So here we're only going to look at supernovae that still have a little bit of hydrogen, haven't lost all of it, and we're going to explode them. And here we get the light curves of single stars on the left and binaries on the right. And so this is time of the supernova. So this is about 4 months. And this is luminosity, which is roughly a supernova outputs as much light in a few days as the sun will output over its 10 billion year lifetime, which is a scary thought. But here, these are all single stars, and you see they're all what we call plateau supernovae, where they've got pretty much the same luminosity before they die away. And this tail is powered by radioactive nickel decaying to iron. On the right, because we've had all those different evolutionary pathways, the supernovae look very different, and they look much muckier. So you still get your 2Ps, but you get some really faint, short evolving light curves. You get something that evolves almost like in a straight line, in a linear light curve, and you get some really long plateaus that look quite weird. And that's the kind of diversity we see in nature. And so actually, by just making these binary models, exploding them, we can immediately see that, you know, supernovae would be very boring if every star was single. We only get the exciting different supernovae we see because we have these interacting binary stars. And this is one thing we're trying to do with BPAS, and trying to get more people to use it, which is difficult, because how do you force people to use it, right? You make it easy for them, which is the work that Heloise has been doing using Hoki. So this is an old screenshot. If you go and search for Hoki from Heloise's GitHub page, there's lots more examples here about the kind of thing you can do. And one example is something I did here, where I took a screenshot of what I was doing in a Linux VirtualBox, comparing, these are basically HR diagrams. They're different axes. This is still temperature, but this is blue, this is red, and this is still brightness. And so this is for Matariki, or the Pleiades. This is Gaia data, where they've looked at every star in the Pleiades, measured its distance, and what its color and its temperature. And if you try and fit an age using single star tracks, you basically have a line, and you have all these stars off here that are obviously like weird. Why are they off at these different ages? If you make the binary version of this diagram where the contours, the shaded contours, are the theoretical version of the observations, you can see that there are darker patches, and that these stars are probably the result of binary evolution. These stars off here, off the edge, are probably because of dust, because if you look at Gaia, they can also measure how much dust these are, and that can also make things look redder if they've got more dust. We're still trying to work this out, and this is work Gleb is doing. But yeah, so both of these are the same age. It's actually younger than the age that most people think for the Matariki, and so we still don't know what the age is. We're going to have to look at that and try and work out how young it is. And this on the left for single stars takes a few seconds to make, and on the right, this now takes about 2 or 3 minutes, which doesn't sound like much, but this is the first time people can actually download, and if they want to make these color magnitude diagrams to do this test themselves, it is now so much easier for them because of the work that Heloise has done, and it only takes a few lines of code because they don't have to work out how to load the models in and do this. So this is what we're really trying to do. So it's not just trying to do good science, it's trying to also make that science accessible so others can use it to provide a useful tool. Heloise has also been doing some other work, and when we're looking at those color magnitude diagrams, how do you judge age of a stellar population? And this is from her recent paper. We're still waiting to hear back the referee report from, where we're comparing those BPAS contours in grey, and these lines are what people have used to try and work out ages. They basically try and eyeball it. They try and say, okay, which one of these coloured lines best matches where all these stars are? And the answer is none of them, right? Because if you try and pick this blue line, because you know this one's pointing over and it's probably going to be matched to that star, but then you can't get these ones, and if you go up here though, then you can't explain that one. With BPAS, you can see with the contours, we can start to understand that yes, this is actually probably the best age that we've presented here, which is 10 to the 6.9, or about 88 million years old, 8 or 9, I can't remember. But again, it's trying to also do things better, and you can see we can do better than just try and say, which line is better. Heloise, in her age wizard routine, has now been able to produce distributions of the ages, so we can actually see when the probability of the age reaches a peak for different star clusters. And again, that's why we've plotted up 6.9 on that plot, because it's got the largest peak, or it's close to the peak of the probability for that star cluster. Okay, right. So how long have we got? We've got about 7 to 10 minutes left. Okay, that's good. I want to stop to give about 10-15 minutes for questions if I can do. So this is the more recent work we've been doing, because now we're trying to think about that entire universe. So what I've talked about so far is looking at very specific objects in the nearby universe, very specific star clusters or very specific supernovae, generally what happens with stars. But let's go back and take that overall picture of the universe, because now observers are pushing back the observational frontiers so that we can actually understand how those stars, we can see further and further into the universe. So we can actually see events earlier in the time, and we can see how, say, the rate of supernovae has varied over the life history of the universe. So how do we, well, observing that is very tough anyway, but how do we model that within the simulation? And so this is something that we've been doing with all my students recently, which is where I've been using the delay time distribution of stars. So when we have our stellar models, we make them all start at the same time, and we look how stars change as they age. And if we have supernovae, we'll record when they happen. So here on these plots, the x-axis is time, and up the y-axis is the rate of events. And so here in red, we have the rate of Cuppa supernovae, which don't occur after about 100 million years. We have another type of supernovae, type 1a. We have other explosions, parent stability, long gamma ray bursts, but also the rate of gravitational wave mergers. And so you can see there's relative rates, because these ones are much less common than supernovae, because every massive star that explodes in a supernova gives you a supernova. But not every star exploding in a supernova will stay in a binary that's short enough or small enough that they can actually then merge within the age of the universe for gravitational radiation, which is why these gravitational wave events are much less likely than the core collapse supernovae. And there's two plots here. This is with solar metallicity, so the composition of these stars is the same as the sun. this on the left, where we've gone to about a tenth of the luminosity of the, tenth of the metallicity of the sun. Metallicity being everything that's not hydrogen and helium, right? You can look up an astronomer's periodic table. There's hydrogen, helium, and everything else. We don't care. I mean, we do care a little bit, but you know, we're trying to get there. So that's what we've been working on before, the delay time distribution, how stars evolve. But that can't be linked. So here you've got observational constraints from looking at galaxies, because there they can look at galaxies, look at how old the stellar populations are, work out the supernova rate. What we've been able to do is add in this with cosmic star formation history. So this is work that we're doing with Petra Tang. And here we can see from the look back time, so how old we're looking into the universe, what's the star formation rate at different metallicities, right? So you can actually see the more metal-rich star formation didn't really start until much more recently. And early in the universe, it was very metal-poor star formation. So all the initial elements that were made were hydrogen and helium, and then it took time for stars to build up metals before we could have stars like our sun. Our sun is probably a second or third generation star, because it's this yellow line is the metallicity, and actually you can see that our sun would have formed around about this point, just as solar metallicity was becoming much more abundant. Okay, so now we've got these two together, so we know when stars die, we know that when the stars were born in the universe, and we can combine them together to make these two bottom plots, which show you the rate of supernovae, rate of different gravitational wave events, versus either redshift, which is what we can really measure, and versus look back time. Now, the interesting thing about look back time is that's model dependent on your model of the universe. So here we actually have to understand the cosmology and take our understanding of how the universe has evolved over the last 13.7 billion years to be able to make these predictions, which means that there's two things we need to understand, not just the physics of the stars, but the physics of the universe, which is where things start linking together, which makes it exciting. Now, this would be great just doing it on its own, but of course there's observations we can compare to. So this is where we're just looking at the long gamma ray bursts and the supernovae, and the observations you can see have huge error bars, because this is tough, because when you're looking at a galaxy or a supernova that's happening at a redshift of like even above 1, they're so much fainter, and you have to actually try and understand that that wavelength of light, normally so bright in the optical, has been shifted in towards the red and sometimes the infrared, and you don't know how many of these supernovae you're missing, which is why even within these rates there's quite big differences between the estimates. But if you squint hard enough and you understand why these ones may be too low, then you can actually make yourself believe that we get about the right number of core collapse supernovae. With the type 1As, there's a big problem here, because exactly what is a type 1A within our models and within the observations is an interesting question, which is work that I've tried to do with Wouter, and that's something we're going to return to, because there's so much variety of white dwarfs. When they merge or when they accrete material, they can have very different explosions. And long gamma ray bursts have a problem, because these are where you form a black hole in your star and you have a jet. And so there's uncertainty in the rate, which is why we have these 3 points as to how wide the jet is. But Ashley Crimes from the University of Warwick has now actually looked at that, and we've actually got a much better understanding of how well we fit the long gamma ray burst line. So that's things we can see. This plot is about things we can't see, because these are the gravitational wave event rates. So this is what LIGO and Virgo have been doing over the past few years. And so here we're looking at the rate of neutron star mergers on the left and black hole binary mergers on the right. And the observed points from LIGO have these open squares. This is again from the paper we had in 2019. On the left, these are all the pre-LIGO estimates of the neutron star merger rate, which vary by 3 or 4 orders of magnitude, which is great for a theorist because you could fit anything. Most pre-LIGO models, we would predict about there be 300 neutron star mergers per cubic gigaparsec, which is actually quite a lot of space. The problem is the LIGO initial results, and even the current ones, push it quite high up to over 1,000. So that's a factor of 3 difference or so from what people thought was the case and what we know the case is possibly today. As more and more get detected, this rate does drop down. But one interesting thing is what John Bray came up with, where we came up with a new neutron star kick, which determines whether the systems remain bound or unbound at the supernova. We can actually boost that rate. And so we're really waiting to see what this new rate is, because when LIGO come out with their third observing run rate, these error bars should be smaller, which will give us a much better understanding of how we need to change our models to try and understand the evolution of these stars. Black hole binaries are okay. And of course, you can see the rate actually goes up as you go out in redshift. So we're actually already past the peak of the most number of gravitational wave events we can see. This is again work done with Petrel, because once we've done the other paper about saying, oh, these are the rates we predicted, we realized that depending on your universe model, how quickly the universe becomes evolved, how quickly your universe becomes enriched with metals, and what your kick model is, you can get wildly different predictions. So these colored lines are all the different predictions, and if we vary the universe, if we vary the enrichment and the star formation history and the kick, you'll get different numbers, with the solid lines being the limits and this dashed dotted line being an upper limit. And one of the key things to take away here is for neutron stars, varying the galaxy, varying the universe doesn't matter very much, but varying the kick matters a huge amount. Whereas for the other things, varying the universe changes things a lot more than changing the kick model. So this is actually starting to show that even though there's all these uncertainties and things we can vary within our model within reasonable bounds, they affect the results in different ways. The really exciting stuff we've been doing recently is with Wouter and Sohan, where we wanted to do the next step on this. We wanted to not just look at the rate of these events, we wanted to look at the masses and seeing if we can reproduce the mass distribution of the events we see. And one of the things is here, the more massive the black holes or the neutron stars when they merge, the easier it is to see those events. And so Wouter spent some time trying to make these plots, which are where the different colors represent different, what we term chirp masses. So these are things that are neutron star masses, and these are some of the most massive black holes we can see. And so this is just the fraction we would detect at each distance. So at very near distances, you detect everything, apart from the very lowest mass things. But there's this horizon where beyond about 2,000–3,000 megaparsecs, you can't detect anything anymore. And what's even more interesting is, even though you may have the same chirp mass, which is like a product mean of the two masses, if they've got a high mass ratio, so if one is very much more massive than the other, that can change how detectable the signal is. And so this is something we've had to factor in to try and understand the mass distribution. We can predict how many neutron star black hole mergers there are in the universe and their masses, but it's whether we can detect them or not is an important question. And of course, LIGO do this, but again, this is all about trying to take our models as close to the observations as we can. And when we do that, we get these plots, which from left to right, they're neutron star mergers, black hole neutron star mergers, and black hole mergers. And so the x-axis in each one of these plots is the chirp mass, going from 1 solar mass up to 100 solar masses on a log scale. And then the y-axis is the mass ratio, going from equal mass binaries at the top down to the lowest mass star is 10% of the more massive star. And the darker contours mean you have more events. The points are from 03, and so, you know, in 02 we wouldn't have detected these peaks, but we may do within 03. These are a prediction. I've got a feeling this peak at our high chirp masses probably doesn't exist, but until the 03 results are released, we won't know. And that it will mean I have to change the model physics in the models anyway, but it's something we're looking at. But also the masses of the black holes you get from your models is model dependent as well. So the other thing Sohan did is he made, I'm trying to work out probably hundreds of these plots, because there was many different ways we've looked at them to try and understand what can change these mass ratios, because again, there's more uncertain physics that goes into them. What changes here between these two is different neutron star kicks. And we'll know this soon. Within a few months, LIGO Virgo collaboration will have released the 03 catalogue, and we'll be able to actually put more points on here and try and understand which one of these best fit the observations. This is work Max is doing, where we're going to be looking also at the galaxies and try and predict. So whereas there we're looking at the entire universe, next step we're going to look at, which is the last couple of minutes, I'm overrunning, sorry everyone, where we're going to look at the galaxies where we see these events go off. And so this is galaxy mass along the x-axis from a cosmological simulation, and Max has worked out for those galaxies how many different supernovae we should see, or different events we should see in these galaxies. For example, if we take this brown line, which is for long gamma ray bursts, there's a really sharp cutoff here. So in big massive galaxies, ellipticals or Milky Way-like galaxies, we shouldn't see any long gamma ray bursts. But in younger dwarf galaxies that are less massive, that's where we should see all the long gamma ray bursts, which is what we see to most degree. Whereas then for gravitational wave mergers, again, they're more concentrated in these high mass galaxies, which are very much older, because with the gravitational wave mergers, it takes a long time for those two stars to merge. So they're more likely to be seen in more massive galaxies. And I can show you an example of that in a second. For the different supernova types, there's also interesting structure in here and how some events become much more common in these massive galaxies and others less common. So again, this is work we're still looking at, but it's where we're now going to the next step, which is to look at the host galaxies of gravitational wave transients. And this is what we got awarded the Marsden Fund for. So this is the only host galaxy we know for GW 170817. So here's the kilonova that was seen from two neutron stars merging, producing something like a Jupiter's mass worth of gold, which is exciting, maybe, I'm not sure. But it's still visible today. I think it's still quite bright in the radio, so people are still studying this kilonova. But this galaxy in the background is what gives us another way of understanding this progenitor, because the age of the stars that merged here must be related in some way to the age of other stars within that galaxy. And by studying that galaxy, we can understand it, or have some constraint on the progenitor. And this is what Andrew Levan did, where he has the spectrum in black of the galaxy. You have this orange model fit, and so you can work out how much mass you have in different ages. Now, the interesting thing is, when Andrew did this, he used single star models, but the kilonova and the neutron star merger was formed by a binary star. So we're pretty sure that galaxy has other binary stars. Elizabeth has done a brief fit, and actually she finds, if I remember correctly, I'd have to go and check the paper where we looked at this, using a very simple way of fitting, just almost like a back of the envelope estimate. This 10 billion year old population is not dominating the light, it's this younger population. And so we're not too sure if this actually exists. And also the metallicity of this younger population is even weaker than what Andrew found. So we don't know what's going on. And one of the reasons why Heloise is now trying to put a code together to do this is because we want to know the answer, because there's information we're losing by not using a binary evolution model here to try and understand this galaxy. We know the differences in age can be very big. Elizabeth did this paper where we looked at elliptical galaxies, looking at their age here on the left. So this is what the ages you get for all these elliptical galaxies if you assume single stars. And with binaries, yeah, this would be BPAS, not BPAS. Anyway, sorry. You get this peak, you get this much broader peak where you distribute the stars over. So we know that there's differences from using binaries. We're still trying to work out what it is though. But the problem is with this, we were just looking at the spectra. To be really sure, we actually need to use what Gleb's doing, which is where this is a cluster where we can unresolve it. So we can just treat the spectra and do a spectral fit. But then Gleb's going to go in and look at all the individual stars we can count in that cluster to give us, see if we get the same age. Because if we don't, there's a problem. But if we get the same age from what Gleb's doing, trying to look at the individual stars and the age of those stars, to what we get from looking at the spectra, we can have greater confidence of our spectral fitting when we then go and look at other stellar populations where we can't count the individual stars. Okay, I think that was everything. I probably left some people out. I think I probably covered everything. But anyway, thank you for listening. And that was some of the things that binary stars do. And I'll answer any questions that people want to ask, even though I can see that no one has asked any questions. So obviously I've answered every question, which is great. Okay, thanks for listening, everyone.
Thank you so much, JJ, for this introduction into the work of you and the Stars and Supernovae group. And I'd just like to point out to the participants of this webinar that if you like to interact, you have 3 ways to do so. You can raise your hand, actually, your virtual hand. I think it's in the participants panel. And in that way, we can actually give you the microphone or online, or you can leave comments or raise Q&A in the Q&A box. So I just leave probably a few seconds for anyone who would like to take the chance to comment, ask questions, or provide any feedback.
Oh, go on. What would you like to add to B pass next? Okay, so the question is, what would I like to add to B pass next? It's a really good question. Yes. Yes. Everything. So the one thing I'd like to add, if I go back, I'm going to have to go back a few slides. Hang on. So one thing I didn't mention, I kind of hinted at it, but I probably didn't mention, is so when you look at this plot, so cold-collapsed supernovae produce mostly oxygen. So when you look at the universe, most of the oxygen in the universe has come from these exploding massive stars, 8 times the mass of our sun. Most of the iron, especially that in your blood, has come from this type of supernova, type 1a supernovae, because these are two white dwarfs merging. They produce about a solar mass of iron each time they explode, whereas cold-collapsed supernovae only produce a very small amount of iron, but not so much of oxygen. Now, if you look at these two curves, the oxygen curve peaks earlier than the type 1a peak. So this means the universe had more oxygen relative to iron earlier in the universe than it does today. And so this has something to do with alpha enhanced abundances. And this is something we really want to try and put into BPAS, because at the moment we take the composition of the sun and we just decrease all the elements at the same ratio, which we know is wrong, but it was the best we could do at the time. So now what we're trying to do is to actually change it so that we put more oxygen in our models of stars from earlier in the universe, both in their interior structure and their atmospheres. And that is actually going to cause a huge increase in how well our models reproduce observations. And we're kind of starting there, and the first models I've made have shown that it makes very little difference to the evolution of the stars, other than the yields and how much, say, nitrogen they produce. But it does make a change to the atmospheres. And when you're trying to model the stellar populations in great detail, you need to be able to understand, make sure your stellar spectra are correct, because otherwise your spectra you predict won't look anything like a galaxy. So that's a really good question, so thank you. How difficult would it be to include several? Okay, several stars. So if you go on Wikipedia and search for multiple star systems, I think the maximum they have is 6. The only 7-star system I'm aware of is called Saga of the Seven Suns. It's a novel series by Kevin J. Anderson. But this is something, the ones we should really probably think hard about are going to be triple stars. Because there, if you have in a binary and you have a star outside going around it, they can actually exchange angular momentum, and you can pump up the eccentricity of the inner or the outer binary. But again, it's a case of, do they just make binary interactions more complex or more common? So my gut feeling at the moment is they make binary interactions more common, but it's still something, people are working on this. So Sylvia Tunen at the University of Birmingham is doing a lot of work on triples, as are Hage Peretz and other people. And they're just, it feels like jumping the gun. We don't really understand binaries yet, so I don't really want to go to triples, but it's something we're doing. Other more multiple systems get more complicated. So if you look at a system you can't understand, that's when maybe you need to start thinking about the porphyries you get from multiple stars like quadruples and quintuples, but the revolution is rare. Also, because if you get one supernova, all those stars are going to unbind, and you're probably not going to keep your system as a multiple. So multiples are important, people are working at it. And of course, the thing is, when you go to like millions of stars, that becomes a star cluster. And so at the other end of this, you've got the cluster people who make n-body simulations of all these stars whizzing around each other. And there, that's really fun, because you get binaries that can exchange stars, and you can try and work out how many, some stars can like change what their companion is several times. And so for these globular clusters, that gets quite good fun. But again, that's computationally intensive, because not only have you got to follow the evolution of a million stars, you've then got to follow their dynamical interactions by n-body calculations, which is hard. But the good thing is, we now have these wonderful GPUs in your laptop that can do that calculation for you. The evolution is harder, so you probably need to treat it approximately. But it's really interesting, some of the stuff they're coming up with. So thank you for that question. I can say I answered that live. I hope that answered the question live.
Yes, you did. Perhaps it's the last question.
Okay, last question from Gleb. How helpful in detecting more mergers with LIGO stuff would it be predict? Well, every merger you get, right, every piece of data you get decreases your error bars a little bit. So what will happen is that when they have the O3 catalog, because they've got something like 50 or 60 events now, the rates are going to be much better known. The error bars will not be in order of magnitude. It will be like with plus or minus maybe 10% or less. So the rates will be very easy to map, or be very constraining. What will be less certain is exactly what the mass distribution and mass ratio distribution, or like the nature of all those mergers and the masses of the two components. That will still be quite uncertain, because again, if you take your 50 or 60 observations, you turn them into one number, you get a very small error bar. If you take 50, 60 observations, spread them over a parameter space, certain areas of your parameter space will be more uncertain than others. But that's interesting. So, but almost it won't be until we have thousands of detections with the 4th or 5th generation gravitational wave observatories will we actually get to the point where you know, we'll be going away from worrying about errors, because we'll know everything. At the moment, each event is worth studying in detail and thinking about on its own, whereas when you have thousands of detections, you start looking at populations. So that's a really good question. Thank you, Glenn.
Right, so we're hitting 3:01, and I just want to say thank you again to JJ for this wonderful webinar. Next week, we would have Jeff Wilmot online, and I hope you are keeping nice and warm on this chilly day, and catch you at 2 p.m. next Thursday. See you, everyone.
Thank you, everyone. Have a good afternoon. Thanks for listening.